Hey Griffin, what are you up to?
Hey Dr. Rehse, I'm just reading this really in-depth manual on the theory behind the shell spectrometer, but it's not entirely clear to me how I actually start to collect data.
Well, we can go ahead and do that. So the first thing we have to do is turn the spectrometer on. And that switch is actually a little bit hidden and hard to find. So it's right on the back there underneath the power plug. Press that. So this is a pretty old version of Windows, but it's easy to launch the software that runs the spectrometer. It's called ESA. It's that icon right in the middle of the page. So why don't you just go ahead and open that. Cool. Okay, so this is the main window. So there's a couple of different windows we might want to open up as we're getting ready to take data. You do that by going to File, Open. We're going to want to open actually a measurement window because you have those data files. So if we wanted to look at data that somebody else had taken, that's for that. The measurement window, we're going to measure some data today. So we're going to want to look at a spectrum. So go ahead and open one of those. But because you're just running it for the first time today, we're also going to want to run a steel calibration. So we're going to want to open up a picture measurement window as well. So go back to File, open another measurement window, but this time make it a picture. And that's going to look pretty different. We're going to need both of those views when we go ahead and try and take the data. Okay, so now you want to switch back to your spectrum measurement. So in Windows, you have to go up to the menu at the top and select Window, Spectrum Measurement. So this is going to be a spectrum from 200 to 840 nanometers, but there's no data in it right now. So we're ready to start taking some data. So you've got to set up the spectrometer for what it is exactly that you want to shoot. So you haven't shot anything today, have you?
No, not yet.
So we have to always run a steel calibration first. So the conditions or experimental parameters we use when you want to shoot a steel calibration are always listed here on the side of the table. So there's a bunch of things that you and I need to understand before we actually can take the data, but we want to make sure the spectrometer is set up to be running all of these things. So if we just go through and look at these, we can see that the laser power was 1.80 watts. You have to have 2 clean pulses. So the laser will fire twice without taking data. So let's go into the software and set that.
Which menu is that under, Dr. Rehse?
So that'll be under Configuration and Hardware Settings. And so here's a window where you can set all the parameters we want to set. And clean pulses is up in the upper right-hand corner. Set that to 2. Now we can set some other parameters at the beginning. We want the number of on-chip accumulations, which we call OCA in the upper left. That, it says, we want set at 1 for now. The gate width tells you how long the camera is open for. We set that to 10 microseconds. The gate delay tells you how long after the laser pulse the camera waits to open, and we want that set at 1 microsecond. For the steel, the amplification is set to 2000. We're not really sure what the units of that are, so always just make sure you look and see what somebody had written down to use the right values. The Q switch delay and system frequency are set for our laser, so you don't ever want to touch those. Okay, how does that look?
Looks all correct up here, Dr. Rehse.
Okay, perfect. Let's go ahead and say OK to confirm that. And now if you look, those exact same windows that you were just editing through the configuration hardware settings are also altered, on that row right there. So you could have made those changes in these windows as well. Just make note that if you change anything in those windows, you have to hit apply afterwards for them to take effect. You can type in that window, but it won't take effect until you hit apply. Those are basically the parameters you need for shooting steel. So you've mounted up a piece of steel, right?
Yes, I have done that.
and you warmed up the laser for 10 minutes, right?
Yes, that has been done.
Okay, so we are basically ready to start the laser. Flash lamps, and we do that by hitting what we call the little lightning bolt button. Okay, fantastic. So with the laser flash lamps flashing, this thing is now actually ready to fire. I'm just turning on some argon in the background. So you are now in control of the spectrometer and the laser. Your very important job is to make sure before you energize and fire the laser at all that everyone in the lab is wearing their laser goggles. When you hit one of the 4 green buttons at the top of the window there, the laser is actually going to fire a pulse. And your job is to make sure to literally scan around the room and make sure everyone has goggles on before you fire the laser. Everything is safe. Make sense?
Yes. Yep.
Okay. So the way you had it set up before, at 2 clean pulses without data and 1 OCA or on-chip accumulation, how many laser pulses do you think you're going to fire if you fire 1 set of measurements, which is going to be the green arrow on the left?
It will fire, I believe, 2 clean pulses, and then 1 to ignite the plasma, so 3 shots altogether.
Right. So when you hit that button on the left, so go ahead and hover over that. It says measure a single spectrum. That's what we want to do. So we're going to hear the laser fire 3 times, or we better, and then we'll see a spectrum appear on the screen, which will indicate that you've actually shot your steel correctly. So I think we're ready to do it. So go ahead and try that.
I heard those 3 clicks.
I did too. Wonderful. Okay, and there's a spectrum of our steel.
Now, Dr. Rehse, is this a normal intensity for these conditions?
This is something you're going to always want to write down in your lab book, and we track that day to day to make sure that we think everything is aligned properly. I think that's a pretty good value for an intensity.
Perfect.
Make sure you consult with your lab mates or the lab book to know what it's supposed to be set.
Perfect.
So say you wanted to save that spectrum. A lot of people aren't familiar with Windows operating systems, so they don't actually know how to save that. So we always want to save some data. So you're going to want to save it. Unlike much of the software you might be used to where it's in the drop-down menu, this is going to be that small floppy disk icon at the left of the screen, that thing. See, if you hover over it, it says save. That's what you want to click on to save. It's a little bit different than systems you might be used to because it is an older operating system. So let's go ahead and save that. So you click save. This will take you into a Windows directory. And if you go to the 2021 data, you note that we always save things with a timestamp. So today is July 16th. So we'll call it 07/16/21. And then you have to click in that folder again. And we always time date our files as well. So we'll call that 07/16/21_1P. And then you say save. So now that file is saved, and now you can actually take that file to the other lab and analyze it whenever you want. It doesn't have to be done on this computer. Okay, so now we can actually play around with some of the other settings, although those are our nominal steel calibration settings. So what happens if we go the on-chip accumulations to 2?
Increase that, and then I'm going to click apply.
So if we do that, you're now going to hear 4 shots fired, but 2 of them are going to be kind of added together to make the spectrum. So we actually expect a spectrum to be roughly twice as big as this one. So let's just see what happens.
Everyone has their glasses on still? I heard.
Sounded like 4. And there you go. So it's approximately twice as big now. It's 50 times. So that's what the on-chip accumulations, or OCA, is. So let's go ahead and set that back to 1. Now, what do you think would happen if we changed the amplification?
I believe all of the intensities would increase somewhat relatively compared to where they are now.
So it's just like turning up the volume on the speaker or the amplifier on your amplifier. So let's make it 2100.
I'm going to click apply. And now we're going to be back to 3 clicks, right, Dr. Rehse?
Correct. Sounded like 3. So now it's 37,000 as opposed to 21,000. So that's a pretty good amount. So it's important to know that there is a limit to how high you can actually set this thing. And it's really important that you don't set that value too high, because this is the one value that really can damage permanently the entire spectrometer. So you're not ever going to want to set that high. In fact, we keep it as low as we possibly can go. So the thing that we're looking for, let's keep turning up the amplification a little bit. We're looking for what's called overflow on the chip. So if we set it to 2200 and say apply, and go ahead and fire that. Now, you see an exclamation point has suddenly appeared.
Yes.
And if you hover over that, that's called pixel overflow. That means you put too much light intensity on the pixels of the camera. And that's not good for the camera. So the rule is, if you're firing one OCA at any target, you should have the amplification set where it's basically not ever overflowing. So you just fired one shot, although we heard 3, but 2 of those were clean pulses. And we fired one OCA, and we got overflow at 2200. So you know that that's going to be too high. So we'll back it down to 2000. That's why the previous students had chosen to take all of their data at 2000. A nice, safe place to do it. You just don't want to damage the spectrum. Now, when we take data, that was one on-chip accumulation, but you see at the bottom of the screen, it says ACCU. Well, kind of confusingly, that stands for accumulations. That's how many different spectra does it add together. And when we take data for our steel calibration, we like to add 5 spectra together. So they don't call it addition, they call it accumulation. So we're actually going to want an accumulation of 5 spectrum. It's like an average of those 5. So let's go ahead and change that. So this, you go to measurement settings. Well, you can look here. I don't see it anywhere on that window, so you can close that. But if you go to configuration, measurement settings, there you go. Now you've got measurement accumulations. It's set to 5. So if you want to do 5, it's already set to 5. Perfect. But now to do that, let's look at the 4 green laser fire buttons up at the top. You are just hitting the one on the left, measure a single spectrum. If you move to the next one over, that's a permanent measuring mode. Let's actually see what that one does. I'll tell you what it's going to do, but then let's watch it. This is going to be a toggle radio button. When you press it, it will stay depressed and keep taking data until you unpress it. So that might be useful if you're actually experimenting and just wanting to see spectra come through. So let's go ahead and try that, just to see what that button does. So it's just going to keep doing this for as long as you keep that button depressed. And like I said, this is useful if you're actually aligning something or you're trying to maximize a target or something like that. It's not saving any of these. It's just flashing through on the screen. So if you wanted to save something, you'd have to stop it and hit that blockade button. So go ahead and stop that now. So we've untoggled the radio button. So that's a very useful mode. So that's the permanent measurement. Now if you go over one more, that's the measure accumulated spectrum. That's what we want to do.
Mm-hmm.
You want to accumulate and get the average of 5 spectra. So you set the number to 5. Now you're going to want to press this button. And then your lab partner will move the steel piece in between each of those shelves. And if you look at the bottom of the screen where it says ACCU, see how that's updating? So that's telling you how many shots were being required. And of course we set it to 5, so it will stop at 5. And there you go. And the important thing to remember about the ESA software is it does not save on its own after taking data. You need to remember to hit that floppy disk button and save that spectrum. What do you think? Make sense?
So, yeah, everything kind of made sense there to me.
So there's one more thing you'll want to do before you start taking the data that you're really interested in.
Okay.
Just checking to make sure that the spectral calibration is correct.
Okay.
The spectrometer doesn't actually measure the wavelength of a line. It just relates the position of the diffracted light to a preset calibration. So we have to check and make sure that that hasn't drifted, which it will do as the lab changes its temperature. So the way you do that is, remember that picture window we opened before?
I do.
Let's take a look at that. So there's your picture measurement tool. Each one of those dots that you see is one of the lines that you were seeing in the spectrum before. So the physics of spontaneous emission tells us that we know exactly where each of those wavelengths should be located. Now we have to figure out what wavelength does the spectrometer think they are. So we'll do that by marking all of the lines that we can for this particular target. This was a piece of steel, so those are most likely iron lines. So let's go ahead and see where the iron lines are supposed to be, and then we'll see if this agrees with that. So if you right-click anywhere, bring up the wavelength table, what's it set for?
Right now it looks like it's reading the oxygen lines.
All right, so we're not interested in oxygen, so let's go ahead to the elements. Brings up a periodic table, which you should be familiar with. Let's unclick oxygen, and you can just click on iron if you want.
Cool.
You could mark them all. That's going to be way too many lines. So you can pick whatever color you want. That might be too dark a color, so you're picking aqua for iron. There you go.
Okay.
Okay. So now you can see in this wavelength table, this is the wavelength and relative intensity of all the lines of iron that the software knows about. So there are a lot. Let's see where they actually line up on this window. So if you say OK,
And how do I bring up those lines on the picture view here, Dr. Rehse?
if you go up to the last set of icons right above the yellow box, the thing at the far right says mark the wavelength. So every one of those emission lines in that previous table is now being marked on top of the camera where those lines are supposed to be. So let's go ahead and zoom in on that. So this picture window is actually showing you what the camera measured. There's a very sensitive CCD camera inside our spectrometer, and it's 1024 by 1024 pixels, and this is what all those pixels are looking at. The blue lines are where each of those emission lines should be, and of course the colored dots is where it saw diffracted light off your Eshelt diffraction rate. So what we're looking for is, do they seem to line up with where they're supposed to be? There's no real scientific way to do this. We just try to look at as many as we can, and you decide for yourself whether you think they're aligned or not. So if you can zoom in a little more on any one of those regions, maybe up at the top, and then work your way down the page, we'll look at these guys. So that looks pretty good. Those ones on the left, there's one that looks centered. You're looking for, do you think that vertical line is centered in the colored region or not?
Some of these look like they're right in the middle.
So that actually looks pretty good. So I would say, yes, this is properly calibrated. It's going to be important because you want the wavelength of the light you measure to be correct.
Now, Dr. Rehse, if this wasn't properly calibrated, where could I go to fix that?
So if you go up to the configuration window, now we're going to a third menu you haven't seen, which we call the pixel shift. So what we would literally do is shift the pixels left or right, or up or down. And left or right is X on the chip, and up or down is Y. In my experience, we never have to touch the Y, but it's not uncommon at all for students to have to change the X pixel shift. And it's a really good idea to do this at the beginning of the day before you accumulate a bunch of data. So if you wanted to really zoom in, that would tell you literally how many pixels over do you want to shift. Why don't we go ahead and take a look at that just to make sure. So if you click out of this window, because you can't really see the pixels here, but zoom in on, yeah, that one right there. Let's zoom in on that even closer. Look, now you can actually see the individual pixels. And then this will tell you, do you want to move left or right? 1 pixel, 2 pixels, a half pixel is allowed. But it's those little box pixels on the screen that tell you how much to shift it. So you really do have to zoom in to this level to see them. And that looks exactly centered as you said.
Right.
So it looks really good. So you can kind of zoom back out on this. And if you're happy with that, you can go back to your spectrum measurement mode. Everything seems to be calibrated. You've taken your steel spectrum. So you're ready to take data for the day.
Awesome.
All right, let's get cracking.